All right, welcome to lesson 4 as we discuss mass transfer. So in electrochemistry, there's three primary modes of mass transfer. We talk about diffusion, migration, and convection. Diffusion is when a species is moving as a result of a concentration gradient. Migration is when a charged species moves under an electric field. And convection is movement that's on the whole fluid that's caused by some more mechanical forces like stirring or pumping, or things like density gradients. And all of these modes of mass transfer add up to give us the total flux in our solution. So we'll have our flux, we'll have the diffusion term, the migration term, and the convection term. So just a little bit more on these modes of mass transfer. Diffusion is all about random movement of species in a solution. And so if you look here, here's this one species and you can see its movement. But when you get a collection of them and there's a concentration gradient, then there's a net movement towards the area of low concentration. That's exactly what happens in our electrochemistry. As we're depleting our reactants at our electrodes, there's a concentration gradient. And so our species will move from the bulk concentration level to towards the lower concentration level at our electrodes. Diffusion occurs primarily at the electrode surface. Migration, on the other hand, occurs everywhere in the solution. It occurs at the electrode surfaces and in the bulk of the solution between the electrodes. Migration is, it's a pushing and pulling of charged species towards a cathode or an anode. So if we have a cation, that cation is going to be pulled towards the cathode, and because the cathode is negatively charged, and it'll be pushed away from the anode, which is positively charged. If we have an anion, then that anion will be pushed away from the negatively charged cathode and pulled towards the positively charged anode. Next, we have convection. Convection occurs in the bulk of the solution, not so much near the electrodes. And this is just the fluid itself moving around. So let's talk about some of the forces that drive mass transfer. Diffusion and migration, they're both caused by a gradient in the electrochemical potential. You might remember that the electrochemical potential is made up of the chemical potential and then some electrostatic forces. And we have a whole video on thermodynamics that dives a little bit deeper into what the electrochemical potential is. But here we can write out its spatial gradient, and that spatial gradient with a constant is what determines the flux of a certain species. And then, of course, we can add on convection that's occurring from stirring and things like that onto the migration and diffusion forces as well. We can do this in one dimension or in multiple dimensions. So let's do a little simple derivation of the Nernst-Planck equation. We're going to derive it in one dimension, and then we'll generalize to multiple dimensions. So let's say we have our flux. We have our gradient of the electrochemical potential with a constant, and then we have our convection term here. We're going to expand out the electrochemical potential term into where we have the chemical potential and the electrostatic forces. And then, we're going to assume that a few things are constant. They're not going to be changing with this derivative. And these are things like the standard chemical potential, the temperature, the activity coefficients, and the bulk concentration, or a reference concentration. These things aren't going to be changing. And so with that, we end up with this equation here. And we can define what our K constant is here. And then we simplify a little bit more, and we end up with the Nernst-Planck equation, where we have the flux, the diffusion term, the migration term, and the convective term. This is in one dimension, and then we can generalize to multidimensional. How does the flux relate to current? So the flux and the current are proportional. And so all that we need is some normalization factors, like the charge of our species, Faraday's constant, and the area of our electrode. And then, of course, we can use the Nernst-Planck equation or simplifications of it to calculate our current. Now, the most important thing is, as you're doing this, is to make sure that you have your signs right. And so you just need to know, where is zero spatially, so that you have a good idea of what's positive and what's negative flux. And then you also need to determine how you're treating positives and negatives in regards to current. So are you saying that oxidative reactions have positive current or negative current? And you just need to define it and then be consistent throughout. So let's talk a little bit more about how the flux is related to current. Let's say we have, here's our current, we have these normalization factors in our flux. We can split out our current into the diffusive, migration, and convective terms, and then split that out into the Nernst-Planck equation. In this case, this is a simplified version of the Nernst-Planck equation. You'll notice we've dropped the convection term. And then we can say, well, these equations were for species J, which is great, but what about the current term, the total current? There's multiple species going on here. And so we just add in summations for everything that's species specific, and that allows us to get the total flux and the total current. So before we end this video, there's a few questions that I want you to give your shot at answering. They are, what are the three forms of mass transport in electrochemical cells, and where do each of these forms dominate? So go ahead and pause the video now, and I'll give you an answer in a few seconds. Okay, so the three forms of mass transport are diffusion, migration, and convection. Diffusion and migration, they dominate near the electrode, and migration and convection, they dominate in the bulk of the electrode. Now, there are things that you can do to your solution to make it so that diffusion is more dominant than migration for a specific species, and we'll talk about that as we go on into the next videos, first of which will be on diffusion.